very rapidly. So the disadvantage, since this material is easy to get, the sand is slowing, and this type of material have the very say distinct or what's it mean? Yeah, this is the biggest disadvantage I think is the high self weight.
It's heavy.
Too heavy. Actually, if you can find some new material have the similar compressive strength, maybe the top building of the long span can make it even longer, even taller. Yeah, this heavy, this weight is very, very important because, as I said, for the large span bridge, there's a strength, actually 90% of that strength was used to resist the self weight. Maybe only not more than 10% of that strength is used to bury the load, the car or other loads. So if you can find some material to resist the self weight to some extent, maybe you can build a longer span of the bridge. But for the concrete, another very obvious disadvantage or something like this. It's the crack. It's easy to crack just because it has a very low tensile strength, so it's easy to crack. And the construction influenced by the climate conditions, and also difficult strength and reconstruction, poor performance of heat and noise. So that's the main content for the concrete, or main characteristic of concrete. And for the concrete, this three indicate FCU, FC, and T. Do you still remember?
Yeah, cubic properties.
Cubic. So what's the size of the specimen to do the experiment to get this value? Which size of the specimen we use?
A cylinder.
The dimension of the specimen or sample.
The dimension.
Yeah, the dimension of the specimen.
The volume.
For this cubic compression series, what type of the specimen we use to do the experiment? But it's cube.
Yeah, cube is three dimension. The volume. The volume.
Yeah, the dimension.
Volume.
I mean dimension.
3D or 3D.
I have an idea what's the way of this.
The length.
The length, yeah, the length. This dimension of this edge of this cubic.
We use the cube. Cubic compressive strength. We use the pressure in the.
Yeah, we need the dimension of the specimen.
Human.
This one? Specimen.
Oh.
Do you remember this word this way?
This is the length.
Millimeter?
Cube.
Cubic.
Oh, times 3.
Yeah.
Yeah. This is actually a cube. The volume of the cube. Is the volume of a cube.
So why these two values difference? Why we got these two different values for the compression strength? Why this one is keep compression strength and this is the actual compression strength? Why? What's the difference?
Because the action will take one direction.
One direction.
But the cube will take
actually, when we do the test, we push compression in one direction.
yeah.
The main difference actually is the size of the specimen is different.
For one we use a cylinder, for the other we use
Riser.
a prize.
Yeah. For this one, extra compressive stress, actually it's also 150 plus 150, but the length is 300. So it's a times for the length. It's not a cube, actually. It is a rectangular. Yes, right. So that's the main difference, not the method of test.
Oh.
So here, test specimen, side length of 150 centimeter cube. And the test condition, temperature is 20 minus or plus 3 degrees. And the relatively humidity of not less than 90% of moist air during 28 days. So this is the standard method, test method, and the Q method. 28 days can finally go to the total, the complete hiding totally. You can go to this, the real strength, because the strength of the concrete actually is gradually improve or with the age of the concrete. Only the age of the 28 days, you can get the real strength. And actually, we also introduced for the FCU, because FCU is used mainly in China, and other countries, American or Europe, they use FC dash. They have this relation because how they got this FC dash? Because the main reason is the specimen is different. Actually, we use the column 6-inch the diameter, and the height is 12-inch is column. The specimen is different, so there's a strength is different. But we have got this relation. Once you know this value, you can go this way, or you know this value, you can transfer to this value. We got this 0.79, this relationship. So this is the actual compressive strength. So you have to go to the textbook. Yeah?
You have the old one?
That's the older version.
I have the old one.
This is the fourth version. This is the third or second. Second.
This latest version.
Oh yeah, this is third, yes. This is the new one.
Yeah.
The office.
So there's a two how say the working what's the 效率怎么讲？中文中效率 what's this? Efficiency. It's too low. Is it?
Yeah.
So actually, those things we have introduced the last class. So we just say again to try to remember it. So this is the test method for the split strings at key. We got two methods to do this test. And the strength and the different stress condition, the result will be different. We will also reduce it. The example is like this. This is the real use in the project. This is three direction with in comparison. So the strength is improved high. So actually, those things we all have introduced. I think, and also we reduce the modulus. Three different calculation methods to get the modulus. The origin elastic modulus, the tangent modulus, and also this deformation modulus. Because you should know modulus actually is reflect the strength of the material. The sigma, the stress we use sigma actually equal to modulus plus epsilon. Okay, so let's see. Modulus actually, if you have high modulus, that means if you want to get very small deformation, then you need to very large load or force. And I think we have finished the material mechanics. EI actually that means the different strength of the section. I is the moment initial, E modulus of the material. So the same section, if you use different material, you can get different strength. So but how to get the modulus actually depend on your calculation method. If you use this method, or use this method, or use this one, the value is relatively different. And besides the elastic modulus, we also can got this GC, shear modulus. Shear modulus actually, once you know EC, and then you know mu, it's mu C.
Partial ratio.
Yeah,
Poisson ratio.
Yeah, Poisson ratio. Then you can get GC. And in Chinese code, we got this formula to calculating elastic modulus by FCUK. That means once you know the compressive strength, cube compressive strength of concrete, then you can use this formula to get the EC, elastic modulus. So this means the different grade of the concrete actually the modulus is different. See, this way you can be 30, 40, 50, 60, something like this. So if the grade is high, then EC is high or lower.
Sorry?
I mean, with the grade of the concrete is improved, will modulus improve or reduce, increase or decrease?
Right. Decrease. And
I mean, with this value increase, will this value decrease or increase?
decrease.
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 Really? Decrease.
Decrease. Wait. Decrease. Because
Yeah, really?
no,
Decrease.
increase. Increase. maybe the F is force there.
Of course, it's increase.
Yeah.
The greed of the company increase. So that means that the company becomes stronger and stronger. So that means the strength becomes stronger. So the modulus, of course, it increase.
Yeah.
So that you don't, you don't need to look at this formula. Just think the greed of the company increase. Of course, the modulus increase. Okay. Okay. So what do you see? Actually, with the grade of the company increase, but the electric modulus actually it changed not so much. Because here it 20, 40, 50, actually this value changed not so large, just little. You can put this different value to calculating to see what's the difference of this different grade of the concrete. Now you can see if you can now calculate if this value is 40 and another value is 60. So that means the compressive strength one is say 40, one is say 60. What's the difference of the modulus? Can you just get this result? Use 40 and 60 to see the difference. How much is it? They increase the not that so much. Divided by 10%. So when the grade increase from 40 to 60, that means the compressive strength actually increased 50%.
Yeah.
Actually, the modulus just increased 10%. And also, we can introduce this stress strain curve for use in different code. Normally, they use this. Why is the increase? Use this curve, and the down part is use the straight line, the oblique line. Actually, in Chinese code, we use a even simple one. The increase part use this quadratic parabola, this curve. And there's no decrease part, just use the horizontal line. That makes the calculation is even easier. Because for the real construction, real project, the decrease part actually is not much use. Because once the concrete, the strain reach this part, actually the concrete already cracked or not cracked. So once the concrete crack, actually when we calculation we don't consider the tensile strength of the concrete. So the mainly useful thing is this part, the increase part. But once you do the research or very special situation, maybe the maybe you have interesting to research this part of this increase part. But for the user real project, it's not much meaning. And also we have reduced the deformation of the concrete. So deformation of the concrete actually one aspect is induced by the load, another is induced by the chemical and physical reaction process, the shrinkage and the creep. So what's the difference between the shrinkage and the creep? Do you remember?
And the difference between
Shrinkage and creep and shrinkage. So creep. Shrinkage. Just remember what's the meaning of creep or what's the meaning of shrinkage? And imagine
shrinkage.
yes, shrinkage. Here, shrinkage. And the creep.
In creep is not to the shrinkage is that is reduce the weight, but the creep is just is like is decreasing. But the shrinkage is like reducing.
Yeah.
But the shrink is not reducing. The two are the deformation, right? For the shrinking is like the concrete is reducing, as for the creep and for the creep is like the concrete is like the surface.
Yeah. Actually, creep is the effect of the loading, but the loading is not changing. It's a non-effect of loading. But shrinkage actually just because of the chemical and physical hardening process, the loss of the water, there's no effect, not constant, no relation with the load. But the creep is related to load, long-term load, long-term load. So the reason of the creep is long-term effect of loading. The water here is gradually pressed out, and the same as gradually viscous flows like this.
And the shrinkage is according to the property of the concrete.
Yes. So it's better to know the real difference of these two deformations. So now we come back to this steel reinforcement. Actually, last class we have reached here, but we didn't much. We have reduced for the reinforcement. We can divide into these two different types: carbon steel and ordinary low alloy steel. And for the carbon steel, depending on the content of the carbon, we can divide into low or middle and high carbon steel. It's good, mainly depending on the carbon content. 0.25% or less is low carbon steel. So with the content of the carbon increase, what will change for the steel
When the
with the content of the carbon increase? And in which aspect the steel have large or various change?
we can break it easy. Crack. Okay.
And
And it becomes stronger. Tell them.
It will be not lasting long time.
with the content of the carbon increase, actually the compressive strength for the steel increased, but the plasticity plasticity decreased. So that means the deformation capacity is becoming poor. It's easy to break. Or so that means the failure would become brittle, not plastic one. Kind of suddenly. Once the load extends some value, maybe the steel break down suddenly. But for this method, we can just divide into this three different types: hot rolled steel, heat-treated steel, and cold manufactured steel. And also, yes, last class we introduced those things. You want to have a read, Bob?
Yeah.
Business brand. But for the situation like this time, say this one, use press C, press where what's it word? What's the word? Is it thick? Claw? No, it's not. It's claw. Thick. Okay, thick. No. Hold the spoon. Yeah, you can use thick or shape. Sometimes cos steel bar, okay? We use this word cos steel bar. See, this is the anchor. So this is the vertical direction in the B. So for the normally for the vertical direction stress, we use this cos steel bar where the dimension is normal 30 or even maybe 40, something like this. So see this tube? Yeah, this is the normally for the longitudinal or lateral relatively very long. I think normally large than 20 meters longer, even several hundred meters longer. So for this, the longitudinal or lateral pre-stress, we use this high strong pre-stress brand. For the vertical pre-stress, we use this cos steel bar to action to put the pre-stress on the beam. So the reason why we for the vertical one, why we don't use the pre-stress brand, why we use this cos steel bar, this rigid steel bar. What's the main reason do you think?
If you use this for one, you need deformation. What is the deformation?
Deformation?
Yeah, we use the big one because I think the big one can resist the friction that can resist easily. But if you use the small one, you can bend.
Actually, it's not small. You see, for those we can use we don't use one, we use a lot. But why we don't use this type? We use the cost still by
I think this one is more art.
Oh, so the one is why we put it in the why we put it in the
I think that's the same thing. Normally we leave the hole first, and after the beam is reaching the space, we put the steel strand, or the strand strand, or the cross with the steel inside.
I think it's because it's more strong.
Most one, yes, more stronger. Yeah, that's the reason. But see, for this type of material, if we use for this short length, once the anchor or the deformation of the pre-stressed strand occurs, or the loose of the anchor, or the creep or the concrete or something like this, the stress loss will, compared with the cold steel bar, the stress loss of this type for this short length will much more than that cost people steel bar. So for this short, for this very short distance, if you want to have a very good effective pre-stress, then this method is pretty good because the anchor is strong and the deformation of this cost steel bar is very, very small. That means they can reduce the stress loss, the pre-stress loss. But for this type of things, the pre-stress loss may be much more than this cost steel bar, cost riveted steel. This is the main reason why for the short distance piece we use this very cost steel bar. And for the long distance, then we can use this pre-stressed high strong pre-stressed strand. So this for the pre-stressed strand one. That's a different thing. See, this for this type, it's made about six wires, or sometimes you made by 2 or 3, and you may find this one by 50 or something like this. So for this cost steel bar, we just have large diameter, maybe 30, 40, something like this, very thick. And the mechanical property of steel bar actually means the stress and the strain is close. The stress and the strain, just like the concrete actually. But we know for the concrete, the stress and strain curve is go like this, go up here and increase like this. But for this steel, you see. At the beginning also is an elastic part, just like the concrete.
Yeah.
When the force is small, the deformation and the force actually is elastic have a proportional relation. Yeah. When the force is large, it increase. And now the curve is not straight line, it become curve. And at this point, Okay, now here is the yielding strength. Now, even the force, if the force doesn't increase, the deformation will increase quickly to here, and then with the increase of the deformation, actually the stress also increases. That means the strength of the steel also increase. At this part, that means the tensile strength of the steel can be increased. So here, which is I think is the ultimate, the maximum tensile strength. After that, then it begin to reduce and generally will break down. So it's different. For the company is that when you reach the high value, the maximum value, and they will decrease directly. But for the steel, when you reach the high value, but this is not the maximum value, and they maybe increase a little bit, and they generally increase to the maximum value, and then decrease. So it's also divided into 3 stages. The OA stage is the elastic stage, and the CD is strengthening stage. That means strengthening the tensile strength of the steel will be strengthened. So this is the property of the steel to handle the concrete. And C, the D stage, necking stage. So necking stage, that means the deformation actually is this part, necking. So the distance, the deformation increases quickly, and then the stress or the strength will be decreased. Then when you reach some distance, this will break. So this diameter is the original diameter. When the steel bar breaks, the diameter at this position is a lot smaller than the original diameter. Suppose the original diameter may be 20, now maybe 10 or something like this. So the necking, that's the necking. So we got for this stress strain curve have 3 points, namely proportional strength, yield strength, and the ultimate strength. This ultimate strength is yield strength, and now we have this position of A point, the proportional strength. And also the same like in the concrete, the steel also will have 2 physical and mechanical things. First one, the strength indices. For B, yield strength. Like this here, for the B, yield strength. And sigma B is the mean basis for design and the calculation for the reinforced concrete structure. So you see, this value, this is ultimate strength. This is the yield strength. This value is much higher than this value. But when we design, actually we use this as the basis, as the strength of the steel. This because see once the steel reach this strength, they have got a process of the strengthening part. The deformation will increase with the strength increasing compared to say companion with the what's the word? the strength increase with the deformation increase. Not suitable to use for design actually. So the point B, yield stress is the main basis for design and calculation. Because the stress or the steel reinforcement reach the yield strength without increasing the load, but strain continues to grow. This makes the reinforced concrete crack too broadly and too large formation of the structure and the structure growth. See this one? At this point, after this point, even the load doesn't increase, the deformation will increase quickly. So that means in the concrete, reinforced concrete, the crack will increase. Once the crack becomes larger and wider, that means that the structure may be filled already. And point D, ultimate tensile strength. That means the highest point. So it's like this. This point D, the ultimate. The ultimate strength. This strength actually is a failure strength of material. That means once the steel bar reach the strength, the load, the stress reach this point. That means it will break soon. Once the stress is large at this, that means the steel bar will soon break.
So Ashwan, it's reaches the maximum point, meaning it's still about to break.
Yeah. So that means that the situation will be very dangerous. It's just the nearly destroyable failure. So this is used to access the large amount of deformation made up the tensile strength of the concrete and cannot be the means of the calculation. Apparently, the equation 17 is defined as the ratio of the ratio of the yield strength of the concrete strength and the ultimate tensile strength, and then can indicate the potential reliability structure. See this ratio. Yield strength divided by the ultimate strength. What's the value in
Ratio.
Yeah. If the value is a larger or it's value smaller good or this value large is good.
Smaller is good.
Why?
Because the all we need C, which there is will be C is good.
No. The ratio is smaller. The structure has higher reliability.
Yeah, this is here. I explain why is high reliability. Why smaller value means high reliability?
When it's smaller, meaning the structure tends to be like how higher strength like to yield loop.
So that's smaller value means that the distance of this point to this point actually this distance is a higher, is larger. So that means after the yield point, the still have a larger, I would say, larger space for to development. So that means they have they can the deformation can yeah. So that means the ratio, this ratio, smaller means higher ability, but it's not means more smaller also means sometimes the waste of material. You cannot use too small a value of this. So that means the distance maybe so high, it's not actually you don't use that's sometimes waste of material. Just control this very reasonable content, reasonable caustic code. What's the name?
For example, ratio.
Yes. So there's also those two plastic in this elongation rate, also known as elongation. 40E corresponding to what's this thing? Abscissa. Measurement go to refer to 5 times or 10 times the bar diameters. So elongation ratio is expressed like this. That means actually it also reflects the plasticity. Yes. So that means the deformation very large or long distance can be kind of deformation. So another index is the code bending properties. So CLR. So code bending properties. So that means the CLR you can bending repeatedly many times. If this index is low, that means maybe you bending several times you breaking. If you have very good code bending properties, then you can bend lots of times. Yeah. So that's another index, code bending properties, which is the performance of the non-cracking. See, the non-cracking, when you're bending, you cannot generate a crack. Non-cracking, friction and brittle failure in the presence of the code friction. Through the code bending test, bending signals the diameter and the angle of the bending. When the specimen surface crack or fracture or node is used to reflect the flexibilities. So this two index, elongation ratio and the code bending properties. And this is the stress strain model, just like the concrete. The real relation between the stress and strain is like this. But when we do the design or use it for the real projection, this is too complicated. It's not easy to use. So we make this simple this mode. Use this two straight line, one the fixed straight line and then horizontal line. Applying the model for the description of the four elastic material is applicable to the low strength theory with long yielding black hole. So this yielding black hole. This model simplifies stress strain curve in this figure. Comparison of two lines mathematically pressing like this. It's a very simple model. See, this straight line actually is just here is elastic proportional relationship from between the sigma and x. So that means this part we use the elastic approaching to calculate it. And after that, after the yielding strength, they just use the straight line to make it so simple. So this is another mode, straight line model. So nearly the same, just after this point, use another straight line or straight line to replace the strengthening part. So straight line mode for description of full elastic plus hardening. Sorry, elastic plus hardening is applicable to smart steel with a short yield platform. And can describe the straight hardening practicing immediately after yielding. So that means this part will be very short. So the stress about the yield string can be correctly estimated, and the model can be expressed like this. It's also very simple mode. Also straight line. So it's a simple. This is another model, much less model. The no horizontal line also brings the bias model for the description of the elastic plastic. Can describe the stress strain curve of the high strength steel reinforcement or wire without segment layer platform. Can be mathematically expressed like this. So that's this actually is suitable for describing the steel with a high carbon content. Because with the content of carbon increase, the plasticity of the steel actually reduced and the strength will increase. Just for this situation, with the high strength steel without a significant yield platform. So this yield platform actually means this steel have very good plasticity probabilities. Probabilities, yes.
Association.
Folklore. How do we have folklore?
Yeah.
Folklore
For close to 4 days. You will start the next class 4 days. So it takes minutes break.
Okay.
Just about this time break.
Let's see, we can add 4:30 and then we end at 6.
Yeah.
Okay.
Chandra. You have any new? Yes, new one. I got yesterday. Hello. Because yesterday I had a new account. What? Two account I have right now. Is it possible? Yes, possible. You're welcome. Oh, masuk ke sini ke kerja lah. Asal kita dapat. Ada tidak kerja. Awalnya harus sudah hasil sana. Sudah dari kita bereaksi. Kita selalu sudah. Pero I think that two ages. I don't. Kemarin kali kita sampai. Ekstra. Salah lagi. Asal itu. Namaste, Yes. Namaste. Oh, iya, tahu. Iya. Ekor gitu. Apa itu? Dua kelas. Fantastic. Fantastic. Why is the place?